Let's talk about ordered pairs. So, I have various things related to this, but it's just kind of a general heading. But starting with the rectangular coordinate system in general, also called the Cartesian coordinate system, it's made up of two perpendicular real number lines, which we say then form a plane. So we're looking at an entire flat surface that we're imagining really is going on forever in all directions. But no matter how big it gets, as long as we have those two perpendicular lines, the origin where they intersect, then any point on that entire flat surface can be identified in terms of how far it is horizontally. So we have the horizontal X number line and the vertical Y number line. How far it is from that origin point horizontally, and then how far it is vertically. That's enough to identify any point anywhere on that entire surface. The origin is 0 on both axes, and then on the x-axis, we have positive numbers to the right, negative numbers to the left, so it's just our standard number line. And then the y-axis is a second number line that's turned 90 degrees, and it's negative numbers going down, positive numbers going up. So I imagine pretty much what you would expect if you were going to try and take a guess on that. So that's the just coordinate system that we're starting with. So then any point on the plane again can be identified by its horizontal distance and then its vertical distance from the origin. The horizontal distance we call the x coordinate and the vertical distance the y coordinate. And we always give them in order, the x and then the y, put inside parentheses, separated by a comma. So we have that format. Don't confuse these parentheses with the parentheses of an interval. An interval with parentheses AB is a starting and an ending value in, but those are on one single number line. So it could be a starting X and an ending X, a starting Y and an ending Y, but they're in one dimension rather than two dimensions. So plotting points you need to be comfortable doing. So looking at these, -3, 2 means from the origin we go -3 on the X, or 3 units to the left of the origin, and then 2 units, the 2 units up. And so we have the point -3, 2. And then 6, 0, 6 units horizontally from the origin, 0 units vertically, puts us here. -2, -2, we get 2 units to the left and 2 units down from the origin. 6, 5, 6 units to the right, 5 units up. As we get that, you can see that lines up with 6 on the X and then 5 on the Y. Go straight lines so you can tell that as you're looking at a point. 0, -3, 0 units horizontally, but then 3 units down is on the y-axis. And then 6, -3 lining up with the 6 on the x-axis and -3 on the y-axis. So notice we have these points on the axes have a 0. So a 0 for the y coordinate means it's on the x-axis, and a 0 for the x coordinate puts it on the y-axis. All right. So then we have equations that have ordered pairs as their solutions. And so these are equations in two variables. They're giving a relationship between the variables x and y. So we have two expressions involving x and y set equal to each other. And so any ordered pair, an x and y combination that makes the statement true, is a solution of the equation. And what we end up typically with these is a whole bunch of solutions. but they're going to follow a certain pattern. So what happens is we come up with the graph of this solution. And unlike if you're solving a single variable equation, the graph would just be one point, a dot marked. Typically, there may be a couple of dots marked on a number line. So you might have something like this. Just a point here or there. And then when it was a solution of an inequality, of a linear inequality, then you maybe had a piece of the number line, possibly multiple pieces of the number line, but still one-dimensional. Now we're going to have a graph that isn't just a piece of a number line. It gets much more complicated when we add this second dimension. A complete graph just shows enough of the graph to clearly represent the pattern that's happening. So if you think about it, if you start plotting points, then you have these separate points, but it's kind of like those pieces of the number line, the intervals. You could come up with individual values that satisfy an inequality, but the whole solution is that entire piece of the number line. The graph of an equation typically is a whole connected line made up of these infinitely many individual points that are all, there's just any gap gets filled in by more points. So we don't plot all the individual points. We plot enough points to see the pattern and to know what the graph is doing, and then we can just draw the line. It might be a straight line or a curve, usually a curved line, that is kind of showing that pattern, right? So what happens is you start to learn with specific types of equations what that graph is going to look like. This type of equation is always going to have a straight line. This type is always going to have this sort of U-shaped graph, and so on. And that way you don't have to plot as many points, because you just know I need this particular part. If it's a straight line, I really just need any 2 points on it, and then I know it's just a straight line, and so on. So you learn what the graph of different types of equations are going to look like, and then use that to help find the complete graph. Typically, we want all turning points in a complete graph, but you might have a graph that does something like it goes just up and down, and then it's going to keep having turning points over and over again, but you just need enough of it to see the pattern. And again, if you know the type of equation, then you would also know whether it's going to keep doing that or not. All right. So one thing you need to be able to do is tell whether a point is on the graph of an equation. And the way you do that is, well, does that x and y value satisfy this equation? So I have the equation 2x minus y equals 6, and I have a ordered pair of 0.23. So an x value of 2, y a value of 3. So I just test if I substitute 2 for x and 3 for y, does that, what I'm testing is that equal sign true? Does that in fact equal 6? Well, 2 times 2 is 4, minus 3 is 1. That certainly does not equal 6. So we know whatever the graph of 2x minus y equals 6 looks like, it doesn't have the 0.23 on it. What about 2, negative 2? Well, I do the same thing. I plug in 2 for x and negative 2 for y, and I want to see if that comes out equal to 6. Well, 2 times 2 is 4, minus negative 2 becomes plus 2, and 4 plus 2 is 6. Sure enough, it does. That's what we wanted it to equal. So that's a yes. Whatever else might be on that graph, we know for sure it has the 0.2, negative 2 on it, right? Now, obviously, you don't want to just start picking random points and test. That would be a very inefficient way to come up with the graph of an equation. So typically what we do is we find some points by picking, typically picking an x value and finding a y value, or you could pick a y value and find the x value that goes with it. But typically for each x value, there's going to be one specific y value that works. So you'll see something like a table of values typically, and we don't start with really obscure numbers. We don't start with fractions or, square root of 2 or something. That we should start with whole numbers close to 0, typically. So in fact, even starting with 0. So I'm going to go 0. I'll go 1. Maybe I'll go in the other direction, -1, and see what seems to be happening with this. So pulling it in for 0, 2 times 0 plus 5 is 0 plus 5, and that's 5. So I have the point 0, 5. And then for 1, 2 times 1 plus 5 is 2 plus 5, which is 7. So I have the point 1, 7, which is here. And then -1, 2 times -1 plus 5 is -2 plus 5, which is 3. So I have the point -1, 3, and that's here. And you might be able to start seeing a pattern with those 3 points. If I go 2 times 2 is 4, plus 5 is 9. I can guess the next point is going to be off my graph and be too far. So I'm going to work back the other way. -2, 2 times -2 is -4, plus 5 is 1. -2, 1. See if you can predict where the next point is going to go. If I go -3, 2 times -3 is -6. -6 plus 5 is -1. -3, -1. So it seems like each time, as I add 1 to the x value, I'm adding 2 to the y value. As I subtract 1 from the x value, I'm subtracting 2. So I can guess I'm going to have points following that same pattern. And this is forming a straight line. This is what we call a linear equation. We have y, we have x, but all that's happening is they're getting multiplied by numbers. They're getting added, subtracted, but there aren't any squares. X and y aren't getting multiplied by each other. All that happens is there's just sort of a y term and an x term and a number. That's a linear equation. It's going to have a straight line graph, and really all you need to graph a straight line is 2 points, but 3 points give you a little bit more of that pattern. So typically you won't always see arrows drawn on the end, but for a complete graph, we just say, well, it's going to keep doing this pattern. And even if I just have 2 points, that's enough for the pattern. I could, just put the arrows. So the arrows don't have to be like all the way to the edge of the graph. They just say it keeps doing what it's doing forever, right? So that's ordered pairs and various applications of what happens when you have an ordered pair or multiple ordered pairs.